Hello students, on the behalf of Maharshi Parshuram College of Engineering Varaneshwar, I Dr. Amit Kumar Mane welcome all of you in the physics lecture series. In today's lecture, we will deal with the chapter Dual Nature of Radiation and Matter. This chapter can be asked for 4 marks and with option 5 marks. So in this session, I would like to cover some important questions related to this chapter. This will help you to write the final board examination. So let us start. Here is the first multiple choice question. An electron and proton are accelerated through the same potential difference. The ratio of their de Broglie wavelengths lambda E upon lambda P is. So here options are given 1, A is 1, B is MP upon ME, C is ME upon MP, and D is under root MP upon ME. So out of this, which option is correct? So let us find it. So you know that de Broglie wavelength for the electron, that is lambda E, can be written as H upon square root of 2 me into E into V, where H is called the Planck's constant, me is the mass of electron, E is the charge on electron, and V is the potential difference. Similarly, for proton, the de Broglie wavelength can be given by the formula H upon square root of 2 mp. Now mass of proton, instead of mass of electron we write mass of proton into charge on proton, that is E, and potential difference. So in the example they ask that the ratio, that is lambda E upon lambda P. So we take the ratio lambda E upon lambda P is equal to, we can write or we put this value of lambda E and lambda P from the above equation. We can write H upon the square root of this 2me into E into V divided by lambda P. That can be written as multiply by square root of 2 mp into EV divided by H. So from this equation you can easily write lambda P upon lambda E upon lambda P is equal to square root of mp, mass of proton, upon mass of electron. So the option square root of mp upon me is the correct answer of this MCQ. Next, the photoelectric cutoff voltage in a certain experiment is 1.5 volt. What is the maximum kinetic energy of photoelectrons emitted? Here options are given. So in order to calculate the maximum kinetic energy of photoelectrons emitted, we know that the photoelectric cutoff voltage, that is denoted by letter V0, photoelectric cutoff voltage is 1.5 volt, which is given, and the maximum kinetic energy of photoelectrons emitted you have to calculate. So the maximum kinetic energy, suppose Ke is the maximum kinetic energy, is given by the formula E into V0, where E is the charge on electron and V0 is nothing but photoelectric as photoelectric cutoff voltage. So if we put these values here, charge on electron, 1.6 into 10 raised to minus 19 coulomb into V0 is 1.5 volt. So if we calculate this value, then it comes 2.4 into 10 raised to minus 19 joule. So maximum kinetic energy is 2.4 into 10 raised to minus 19. So 2.4 into 10 raised to minus 19 is the option A, which is correct option. Next, explain what you understand by the de Broglie wavelength of an electron and derive an expression for de Broglie wavelength. The many times this question asked in March 2022, July 2022 for 3 marks. So let us first explain what is mean by the de Broglie wavelength of an electron. So the scientist de Broglie in 1924, he postulated a de Broglie hypothesis, and it can be stated as, according to de Broglie, the matter waves or matter behaves like a particle when not in motion, that is called the steady state, and it is behaves like a wave when it is in motion. What it means? It means that if there is a matter means any entity which has mass and which occupies the space, that is called the matter. So that matter behaves like a particle when not in motion, that means when it is in steady state, then that is act as a particle, and when this particle goes into the motion, then the wave is associated with it. That means when matter is in the motion, it is associated with a wave. That hypothesis is known as the de Broglie hypothesis. You also remember here that de Broglie concept or de Broglie wavelength is an important concept while studying the quantum mechanics. Quantum mechanics is a branch of physics which deals with study of microscopic properties of the particle. Microscopic means the particles which we cannot see by our naked eyes. So they are called elementary particles also. So quantum mechanics is the study of very minute particles like electrons, protons, neutrons, or atoms. Here, this de Broglie wavelength is associated with the wavelength and its relation between the momentum and mass. So the mathematical form of de Broglie wavelength lambda is given by h upon p, where h is called the Planck's constant and p is called the momentum, or this equation can also be written as h upon mv, where momentum is nothing but the mass into velocity. So mass of a particle into velocity of a particle is momentum. So this equation is the mathematical form of the de Broglie hypothesis. Now they also said to derive an expression for this de Broglie wavelength. So let us derive this equation here. Let us see, in order to derive this equation, you know the Einstein's mass energy relation, that is E is equal to mc square. that energy is equal to mass of a particle into c is the velocity of light. Also, suppose that this is equation number 1, and you also know that Planck's equation, that is energy E is equal to h nu, where h is Planck's constant and nu is the frequency of radiation. Suppose that this is equation number 2. Now if we compare these two equations, the left hand side of these equations are same energy, so we can equate the right hand sides of the equation. So we can write the equation mc square is equal to h nu. Here nu is the frequency of the radiation, so frequency can be written as c by lambda, where c is the velocity of light and lambda is the wavelength of the wave. Now if we put this value in this equation here, so we can write mc square is equal to h c by lambda, hc by lambda. Okay. Now if we write this equation for wavelength lambda, then we can write hc upon mc square. So this term goes to this side and this term goes to the denominator. Here if we simplify this equation, that this c is the velocity of light and here is also velocity of light, so one c get cancelled, so remaining is lambda is equal to h upon m into c, and here h is the Planck's constant, m is the mass of the particle and c is the velocity of light. So you know that mass into velocity is the momentum. Momentum can be written as mass into velocity. C is the velocity of light, so mass into velocity is momentum. So we can modify this equation as lambda is equal to h upon mc or equal to h upon p, and this equation is known as the wavelength of de Broglie wave or matter wave. Next, here the photoelectric work function for a metal is 4.2 electron volt. Find the threshold wavelength. The question was asked in March 2022 for 2 marks. So here to solve this example, first of all we write what are the given quantities here. So photoelectric work function for the metal is 4.2 electron volt. That means photoelectric work function is denoted by phi 0, and which is 4.2 electron volt. Now it is in electron volt, we can convert this into joule. So we have to multiply this with the charge of the electron, that is 1.6 into 10 raised to minus 19 is the charge on electron. So this will convert into electron volt to joule, because electron volt is a CGS unit, joule is the SI unit. So we are converting this phi 0 into joule. So if we calculate this, then you will get the answer 6.72 into 10 raised to minus 19 joule. Okay, so this is the value of phi 0. Also the velocity of light, you know, 3 into 10 raised to 8 meter per second, and h is the Planck's constant, which is 6.63 into 10 raised to minus 34 joule second. So we know these quantities in this example. So the photoelectric work function, we want to find out the threshold wavelength if photoelectric work function is given. So the relation between photoelectric work function and threshold wavelength is given by phi 0 is equal to hc by lambda 0, where lambda 0 is known as the threshold wavelength, and here lambda 0 can be written as hc upon phi 0. Now if we put these values in this equation, we get lambda 0 is equal to h is 6.63 into 10 raised to minus 34 joule second into velocity of light is 3 into 10 raised to 8 meter per second divided by phi 0. Phi 0 is 4.2 electron volt, but we have to convert it into joule, that is 6.72 into 10 raised to minus 19 joule. So if we simplify this equation, then we can write as here 6.63 into this 3 is 19.89 into 10 raised to minus 34, and here 10 raised to plus 8, it becomes the 10 raised to minus 26 divided by this 6.72 into 10 raised to minus 19 as it is. So lambda 0 is equal to, if we again simplify this, if this term goes into the numerator 10 raised to minus 19, then can write 19.89 divided by 6.72 into 10 raised to minus 26. If it goes into the numerator, then it becomes plus 19. So minus 26 plus 19, that is minus 7. So if we calculate this value, then it comes 2.959 into 10 raised to minus 7, and the unit is in meter wavelength, or this lambda 0 can be written as 2959 into 10 raised to minus 7, so into 10 raised to minus 3. So we can write this lambda 0 is equal to 2959 into 10 raised to minus 7 into 10 raised to minus 3. It becomes 10 raised to minus 10 meter. So lambda 0 can be written as 2959 10 raised to minus 10 meter means Armstrong. So the value of threshold wavelength which they ask is 2959 Armstrong. Next, the threshold wavelength for silver is 3800 Armstrong. Calculate the maximum kinetic energy in electron volts of photoelectron emitted when ultraviolet radiation of wavelength 2600 Armstrong falls on it. So here again you have to write first the given quantities. The threshold wavelength, that is lambda 0, is given, that is 3800 Armstrong. So that can be converted as 3.8 into 10 raised to minus 7 meter. Again, for ultraviolet radiation, the wavelength is given, suppose that is lambda, and it is 2600 Armstrong. So we can convert this 2.6 into 10 raised to minus 7 meter. Again, you know the value of h, that is Planck's constant, velocity of light, and charge on electron. So it is, the Planck's constant is 6.63 into 10 raised to minus 34 joule second, velocity of light is 3 into 10 raised to 8 meter per second, and charge on the electron is 1.6 into 10 raised to minus 19 coulomb. So these quantities are known to us. Here, according to the Einstein's photoelectric equation, the maximum kinetic energy emitted by electron is given by kinetic energy, which is maximum kinetic energy, is given by the formula h nu minus h nu 0, where this h nu 0 is called the threshold frequency. Now you know that nu can be written as, that is frequency can be written as c upon lambda. So if we put this value of nu is equal to c by lambda in this equation, then kinetic energy, maximum kinetic energy, is written as h into c by lambda minus here c by lambda 0. If we take common c from the bracket, so hc into 1 upon lambda minus 1 upon lambda 0. So if we put this values of h, that is 6.63 into 10 raised to minus 34 into 3 into 10 raised to 8 meter per second, and this bracketed term is 1 upon lambda value is here 2.6 into 2.6 into 10 raised to minus 7 minus 1 upon 3.8 into 10 raised to minus 7. So if we simplify this term, and we will get the answer in, directly I write the answer here, that is 1.510 electron volt. So this is the kinetic energy, maximum kinetic energy is 1.510 electron volt. So thank you for watching this video. I hope you understand the concept of this chapter. Thank you.